Okay, here we have an orbit question where we've got the moon in orbit around the Earth at a distance of 385,000 kilometers, and we want to figure out what speed the moon must be traveling at. So you can see from the picture, we've got a tangential velocity as the moon moves around the Earth, and there must be some force preventing the moon from moving in a straight line. So this is just a dynamics question. If I draw just the moon, and let's imagine it's at the position we see in this diagram, the only reason why it's not moving in a straight line is that there's a force acting at a right angle. And this imaginary string, I guess if you will, that's keeping it to the center of the Earth is the force of gravity. So if that's the only force that's relevant on the moon, that would mean my net force is the force of gravity. But because this is moving in a circle, we say that the net force is the centripetal force. So for any orbiting object, could be a satellite, could be the Earth going around the sun, that's always our starting point. Now, F net is ma, and Fg we have to use the more universal equation. Now, because you're moving in a circle, the acceleration that we use is the centripetal acceleration. So this acceleration that acts towards the center always, we say is the centripetal. Now we have a couple of choices for centripetal acceleration. One that involves the period of motion, and one that involves the velocity or the speed, the tangential speed. Now obviously this is asking us for the speed as the moon orbits, so we want to use the version that has v in it. So I'm going to get mv squared over r, where r is the radius of my circle that I'm orbiting in. That'll equal g m1 m2 over r squared. Now this r is the distance between these two masses, because this is the force of gravity. Just so happens that the distance between the two masses is the orbital radius, which is usually the case, but just be careful, right? Know the definitions of those two r's. Now the object that's in motion, the moon, the one that's attached to the velocity, cancels, and all that's left is the mass of the attracting object, the Earth, at the end of the day. So when I finish the equation, I've got r and r squared both on the denominators on either side of the equation, so I can cancel one of them off. I get v squared is equal to g mass of the Earth over r. So if I want to find v, I have to take the square root of all this. So they give you all the information. I'll finish it over here on the left. So my velocity will be g 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. Times the mass of the Earth, 5.98 times 10 to the 24 kilograms. And I've got to divide all of that by r, the radius of the orbit, which they're telling us is 385,000 kilometers. But we need to get that in meters. So we have to tack on 3 zeros, right? 1,000 meters in a kilometer. So it's actually 385 million meters. So that's 3.85 times 10 to the 8 meters. And if I crank all of that out and take the square root of everything that we see here, I get the velocity of the moon as it's orbiting the Earth is 1,020 meters per second.